In this next section, we're going to look at the second method of transfer of heat, and that is the transfer of heat by radiation. And we all know what radiant heat is. We go out in the sun and it feels warm. That's because the radiation from the sun, both in visible light and in particular, the infrared, warms us up. In fact, all of the radiation that gets absorbed in our bodies turns to random energy and heats us up to some extent, but predominantly the spectra is in the visible light and in the infrared. Now, how do we absorb or transfer heat by radiation? Well, the radiation is going to be by two processes, the process of emission and the process of absorption. Let's look at this process of emission. The profile of emitted radiation is going to be dependent upon the temperature of the object. And we're familiar with substances that emit the infrared because they're hot. In fact, we can heat a poker up and make it feel warm, but we can't see it glow. And then we can heat it hotter and it'll glow red. Then if we heat it more, it'll glow white hot. If you could get it hot enough, it would even glow blue. And that's why our stars appear red, white, and blue, because of the different temperatures they have. These are the cool stars, these are the much hotter stars, and these are the extremely hot stars, the blue ones. The formula for radiation emission is relatively simple, but it is very unusual. This is the formula discovered by Stefan and Boltzmann, and we're going to be looking at an area of material, and so it's going to be an area A, and this area is going to have a temperature T, and it's going to emit radiation. You can say, well, gosh, what if it's cold? It doesn't matter what the temperature is. Every substance emits radiation. It may also absorb more than it's emitting, but even something like ice is constantly emitting radiation and losing heat by its radiation. And what we're interested in again is the amount of heat radiated per unit time. So how much energy leaves the substance per unit time? Well, that depends upon several things. If the area is twice as great, then you'd say it would be twice as great, and that's obvious. If the temperature is twice as great, you might think it's twice the linear with the temperature. This is where it'll really fool you. The radiation depends upon the temperature in Kelvin. Remember, this has got to be in degrees Kelvin, to the fourth power. This is the only place that I know of where we have something that unusual, a power of, and especially T to the fourth, that the radiation is associated with the emission of a given object. There are two other constants. One is a universal constant, sigma, and this is called the Stefan-Boltzmann constant. And it's the same for all substances. And then you have something particular to this substance, and it's how good an emitter this thing is. And this is called the emissivity. And this letter here is epsilon. It looks a little bit different written here. This is the emissivity, E-M-I-S-S-I-V-I-T-Y. And the emissivity of black things, which are very good radiators and very good absorbers, is 1. And the emissivity goes down to 0 for highly polished metal like gold or silver. And of course, they emit almost nothing. They also absorb almost nothing. And sigma, this Stefan-Boltzmann constant, is 5.67051 e to the minus 8. Kind of easy to remember. 5.67 e to the minus 8. 5678. And this is the constant sigma, Stefan-Boltzmann constant. You do not have to memorize it, but you certainly have to memorize this equation, which is very important because it has to do with the radiation of any kind of substance. And of course, what you do is it's easy to know what the temperature of something is. It's pretty easy to compute its area. It's more difficult to know what the emissivity is. If it's a black substance that's like tar or a pitch, then its emissivity will be 1 if it's black. And it'll be 0 if it's shiny metal. And in between, we get all of the others. So it can only go from 0 to 1. It can't get any greater than 1 or any less than 0, obviously. And so this gives us our emissivity. And that's really all we have here. You have to look at different substances. And someone would give you on the test what the emissivity was. Or if you had to guess, you might guess something like a 0.5 for something. You have to estimate how much emissivity it is between black and shiny metal. Is it predominantly very, very dark? And you'll notice that something comes into play here. When we do our house construction, we build our houses, we do something really horrible. We build our roofs so that they're black, for the most part. Now, you can find some shiny metal roofs. The ideal roof would be what? It would be gold foil or polished silver. Then what would happen? In the winter, the house would not emit anything. You'd have no emission outward. You'd have no absorption in the summer. So if it's not going to absorb and not going to emit, that would be a shiny roof. But what do? We make our roofs all black, which is the worst we can possibly do. So in the winter, we lose as much heat as possible, and in the summer, we absorb as much as possible. That's because we think black roofs look good. But if you go to barns and some commercial buildings, you'll more and more find that people are using shiny metal or some other raised tin construction, and often that raised tin construction is very expensive, or raised metal roofing. So this is what you need to do to compute the emission of substance. And if we had just, say, a square of asphalt, maybe let's work a problem. Maybe it measures 2 meters by 2 meters, and it's pretty hot. Let's say it's about halfway up. Let's say it's 40 degrees Celsius. It's, that's pretty good, pretty high temperature, this hot asphalt. And we want to know what is delta Q over delta T. And here, normally this Stefan Boltzmann constant, if you look at it, is going to be given in joules per square meters per degree Kelvin. And we don't usually use the BTUs in hours, although you could convert it back to that. So this would be given by sigma, which would be 5.678 6.7 e to the minus 8. And you're going to multiply that by emissivity, and it's going to be close to 1. You might put a 0.9 there if it's not perfectly sooty looking asphalt. And you'd have an area of 2 times 2 is 4. And then what would your temperature be? Well, I said 40 degrees Celsius. You've got to add that to 273.15. So you're going to add 40 degrees to that, 313.15 to the 4th power. That number has to be taken to the 4th power. So therefore, although this number is very, very small here, you can see this number gets very, very large quickly as I get to higher temperatures. And that would be the emission. And often you can find yourself, we had this in one of our physics books, here's a doctor's office, and all of us have experienced being in a doctor's office. Here we sit in the doctor's office with maybe only our underwear on or something, and we get very cold. That's because our body is radiating outward in every direction, and our body is going to be what? Well, Fahrenheit-wise, it's going to be about 98.6, but the room is probably going to be about 68 degrees, 69 degrees. We could round this to 99. That's 30 degrees difference. And if you look at that difference of how the walls are emitting and how our body is emitting from 99 degrees, the walls are emitting at 69 degrees. So there's a net heat loss away from our body that you can easily compute and assume that the human body has, say, an emissivity of about 0.5, and it might have an area of, say, of 1 square meter. You can estimate those a little bit more accurately and see if you can do that as a homework problem.